Everyone, and welcome to the 7th video about abstract algebra. And in this video we will talk about, as we also said in the last one, cyclic groups that we introduced in the last lecture. So the reason why we're so interested in cyclic groups at the moment might not be very clear, maybe because we're still at the beginning, but we will see that cyclic groups play a very important role in the theory of finite abelian groups, which is a big part of group theory. And for this reason, we are really interested in studying their properties. So in this video, we will do precisely that. In fact, we'll prove some results that hold in general for cyclic groups. So the first fact that we are going to prove is the following. So let's suppose G is a group. And let's suppose A is an element of G with infinite order, which we can denote it like this, which if we want to, we can denote it like this in a more shorthand notation. Then we will have that A to the M will be equal to A to the N if and only if M is equal to N. So let's prove it. So the proof, as you might imagine, is not difficult. And let's prove the reverse direction first. So we see that for the reverse direction, this is trivial because we're multiplying, well, if M is equal to N as integers, then we're trivially multiplying A and by the same amount of times, and so they're trivially equal. And if they're negative, of course, we're multiplying the inverses, but it's the same reasoning. So let's just prove the forward direction. In particular, let's see, so if we have A to the M is equal to A to the N, then by applying A to the minus 1 on N times to the right, what we will get is A times A to the M times A to the minus 1, and then A to the N minus 1, and doing this N times will yield A to the M times A to the minus 1 to the N is equal to the identity. We can rewrite this as A to the M minus N is equal to E. But now we suppose that A was an element with an infinite order, meaning that A to the L is equal to E if and only if L is equal to 0, because if L was not equal to 0, if in fact L was not equal to 0, then what we will have is that the order of A would be L. And so this will contradict the fact that A has infinite order. So for this reason, we require that M minus N is equal to 0. But saying that M minus N is equal to 0 is the same thing as saying that M is equal to N. And so from this, with this, we have concluded the proof of this theorem, which again was very, very quick. So another important fact that we want to prove is the following, and this is about elements with finite order. So suppose that we have again A that is an element of G with finite order. This time we could say order N. Well, then we want to show that the cyclic subgroup generated by A is given by E, that is A to the 0, then A squared, up to A to the N minus 1. And so this is the same thing as saying that the order of this cyclic subgroup generated by A is equal to the order of A, that is equal to N. So this is basically the same assertion. So let's prove this fact. And this actually is what we mentioned in some, I think, 1 or 2 videos ago, this relationship about the order of an element and the order of its cyclic subgroup generated by it, which is a pretty important relation that I'm sure you noticed already, we could say empirically before. But so in order to prove this equality, we will ideally want this set here to be a subset of the cyclic subgroup generated by A, and we also would want the cyclic subgroup generated by A to be a subset of this set here. So we start by proving this inclusion here, which is trivial. In fact, we see immediately that this is true. In particular, it is true that the set given by the identity A squared up to A to the minus 1 is a subset of the cyclic subgroup generated by A. And this follows immediately from the definition of cyclic subgroup generated by A. In fact, it is defined as basically the powers of A inside the group with respect to the multiplication of the group. And being these, of course, powers, of A, it is trivially true that this is a subset of this other set. So we have proven one direction. For the other one, we will have to do some more work, but it's still pretty simple. So we suppose that we have a general A to the L inside our cyclic subgroup generated by A, because we know that, of course, an element of this subgroup is in general of this form here, so we can call it A to the L already. But we really impose no restriction on L, besides it being an integer. Again, calling the order of our element A n by the division algorithm, which is a fact, a pretty important numeric theoretic fact, we can express our L. We will be able to find integers q and r, the quotient and the remainder, respectively, in the integer, such that L can be written as n times q plus r, where r is less than n and greater than or equal to 0. So, with this in mind, we will write our A to the L as just A to the n times q plus r, which is the same as A to the n times q times A to the r. Okay, but now what we see immediately is that since the order of A is n, then A to the n is the identity, and we can write this as A to the n to the q times A to the r. But A to the n to the q is just the identity to the q, the identity of the group, to the qth power times A to the r. But this is just A to the r, because the identity times itself is the identity, and the identity times q times itself is, of course, the identity again. And so let's see what we have got here. We have reduced A to the L to an element of the form A to the m, where m is bit less than n and greater than or equal to 0. In other words, A to the L is an element of this set here. But this is precisely what it means for a set to be a subset of another one. So we have obtained the other direction. Why? Because, well, we proved that for a general element of this subgroup, then it is an element of this set here. So the cyclic subgroup generated by A, this Langle A wrangle, if you want to use like LaTeX notation. So this subgroup here is a subset of this. And so we have this other inclusion relation, which grouped together with the one we proved earlier yields that the cyclic subgroup generated by A is just given by a squared dot 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 up to a to the minus 1. So this concludes this proof. And of course, as an immediate corollary of this, it follows that the order of the cyclic subgroup coincides with the order of A, and it is equal to n. Now, another pretty important fact that it must be surely proved is the following. So again, let's suppose that G is a group, and let's suppose again that A is an element of G, and with order n. Well, then we will have that A to the m is equal to A to the L, where m and L are integers, if and only if n, which is the order of A, divides m minus L. Again, here the proof is pretty simple and straightforward. We will start by the reverse application because it's the easier one. So let's suppose that n divides m minus L. In other words, we know that m minus L can be written as n times x, where x is an integer. Okay, but then we have that a to the m minus L can be written as a to the n times x, which is the same thing as a to the n to the x. Okay, but a to the n is the identity, and so this is equal to the identity times to the power of x, but the identity to the power of x is just the identity. So now we have this relation here. Now multiplying both sides by a to the right and L times will yield a to the m minus L times a is equal to a, but this just becomes minus L plus 1, then a to the m minus L plus 2 a squared dot 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 up to the point of having a to the m minus L plus L is equal to a to the L. And at this point we just get a to the m is equal to a to the l. And so we have proven the reverse implication. For the forward implication, on the other hand, what we will do is we will suppose that a to the m is equal to a to the l. So if that is the case, by consideration we made earlier too, this implies that a to the m minus l is equal to the identity. Okay, but now using again the division algorithm, we will find integers q and r with r less than n and bigger than or equal to 0, such that m minus l can be written as n times q, n times the quotient plus the remainder. Now rewriting this expression using this equation here, this yields a to the n times q plus r is equal to e. In other words, a to the n times q times a to the r is equal to e. Okay, but a to the n times q is just equal to a to the n to the q. But that again is the identity to the q, which is the identity. So this reduces to a to the r alone. And so the equation that we have now is a to the r is equal to e. But notice here we restricted our r to lie between strictly on one side. So it is strictly less than n, but it can be 0. And we know that the only integer in this set, so the only x in this set here, that satisfies a to the x is equal to the identity is x equals 0. Well, why? Because well, if we consider positive integers, and positive integers plus 0 in this case, starting to count, excluding 0, the least positive integer for which this holds is n, meaning that if we ignore 0 here, then we take 1, 2, 3, up to n minus 1, no integer will actually satisfy this. So the first one that will is n. And so we have no other choice but to pick 0. And so we will put r to be equal to 0 here. But let's see what this implies. R being 0, of course, implies that the remainder of the division is 0. In other words, that that n divides m minus l. Okay, but this is exactly what we wanted to show here. And so we have concluded our proof. Now, this proof has many immediate corollaries. So one of it is the following. And the meaning of this corollary is pretty intuitive. I'm sure you can agree with me. And that is that, again, being G a group and all the suppositions we made earlier, being A an element of G, and having order n, then if A to the k is equal to the identity of the element, this will imply that n will divide k. So for the proof, this is very, very simple, because this is just, this is just a special case of the fact we proven earlier. In particular, placing m equal to k and l equal to 0. And we'll divide k minus 0, which is of course just k, and so we have that n divides k. And so this proves this corollary. Fact that is also a corollary of the things we proven earlier is the following. In particular, let A and B be elements of a group such that A times B is equal to B times A so in other words, two commuting elements of a group. Then we will have that the order of their product will divide the product of the orders. So how can we prove this? Again, this is pretty straightforward. So we know that A times B equals to B times A implies that A to the B to the L is equal to A to the L times B to the L. So now, a specific choice for our L. In particular, we will take our L to be the order of A times the order of B. And this will yield the following. By using the equation above, we will get A to the order of A times the order of B times B to the order of A times the order of B. Okay, but now, of course, but this is just A to the order of A to the order of B times B to the order of B to the order of A. But these two just become the identity. And what this is in general, this is just the identity. Okay, but now what we have noticed is that A to the B to the order of A times the order of B is equal to the identity. And this implies that the order of AB divides this exponent, which is the order of A times the order of B. And this concludes this other proof. So now that we have developed a little bit of the theory and we have proven some abstract results, we now want to work a little bit with some examples. But before we work with some examples, let's give a definition really quick, and that is of a generator of a cyclic group. So if you recall, in the last video we defined a cyclic group. We said that a group G is cyclic if there exists a G in C, a small g in G, such that G is equal to the subgroup generated by G. Now, in this case, we call such G a generator of G. And also be careful about not thinking erroneously that generators are unique or something, because groups can have multiple generators. So as an example, in the last video we talked about the integers, which is we will later classify it as an infinite cyclic group, has two generators, and that is 1 and minus 1. Let's look at other examples of cyclic groups and their generators. And now we will use these examples to kind of build up the intuition and the heuristics for the results that will, because of course I think that introducing results and showing the proofs without actually building the intuition behind them beforehand is a little bit unnatural, we could say. So let's consider the group, for example, the addition modulo 8 group. Okay, we know that this group as a set is just formed by 0, 1, 2, 3, 4, 5, 6, and 7. Now let's look a little bit at the subgroups generated by its elements. Okay, what we see is that, well, the subgroup generated by 0, by the identity, we know this already in general, it is just the trivial subgroup. It's just given by 0. The subgroup generated by 1 is Z8 itself, because while 1, this is given by basically m times 1, where m is an integer, and then here of course we have that contains every element of the set, because 0 times 1 is 0, 1 times 1 is 1, 2 times 2 is 2, and so on and so forth. And then when it reaches 8, it just starts over. So its order is 8, because 8 times 1 is equal to 0. So now let's look at 2. So the subgroup generated by 2 is the following: 0, 2, 4, 6, and then 0 again. So 2 has order 4, because 4 times 2 is equal to 8. Then let's look at the subgroup generated by 3. That is 0, 3, 6, 1, 4, 7, and then 2, 5, and then goes back to 0, because 5 plus 3 is 8, and so the order of 3 is 8. And the cyclic subgroup generated by 3 is again the whole set, Z8. So now I will write the cyclic subgroups generated by the other elements, and you can quickly check that they are in fact what I will write. Okay, so these are all the cyclic subgroups, and now we want to notice something, and it is at this stage it's just a little bit of heuristics, a little bit of hypotheses and playing around. But what we want to see is that, well, look at this trend. So the elements which are relatively prime with respect to 8, so in other words the elements such that the GCD of M with respect to 8 is 1, span the group. So in other words, they're generators. In fact, look at this. 1 is relatively prime with respect to 8. 3 is relatively prime with respect to 8 and it spans the group. 5 is relatively prime with respect to 8, and 7 too. And they all are generators. But for example, look at 6, 4, and 2, which are not relatively prime, because they share a divisor, of course. In particular, 4 divides 8, 2 divides 8, and 2 divides 6, and 2 divides 8. So they're all not co-prime. And in fact, they are not generators. So maybe this is just a coincidence. So maybe let's look at another example. Maybe that will help us. So maybe let's look at the example maybe Z9, okay, which is given by 0, 1, 2, 3, 4, 5, 6, 7, and 8. Let's build the cyclic subgroups generated by each one of its elements. I'll do it again. I will skip the calculations because, I mean, they're a little bit trivial, so I'll just present the end results. Okay, so these are the cyclic subgroups generated by each one of its elements. And, well, look, here we notice the same exact trend as before. In particular, the elements which are co-prime with respect to 9, in other words, 1, 2, 4, then 5, 7, and 8 are generators, and they are co-prime. The elements which are not co-prime are not generators. And, well, at this point, it is pretty evident that it's maybe not just a trend, it's maybe a general theorem. And so let's see if maybe we can prove this in some way. For now, we want to prove that if we have k in Z of n, then k generates Zn if and only if the GCD of n with k is 1. So this is the current theorem that we will want to prove. When we'll introduce the notion of isomorphisms, we will see that all cyclic groups behave like either Z or Zn for n, for a positive integer n. So, but this result actually holds in general for finite cyclic groups. So, in order to prove it, however, we will prove this following result first, and we will then see that these two assertions that we made follow as immediate corollaries. So the theorem is the following. So let A be an element of a group as usual, and let its order be equal to n. Now let L be a positive integer. Then what we will have is that A to the L is equal to the so the cyclic subgroup generated by A to the L is equal to the cyclic subgroup generated by A to the GCD of L and n, and that the order of A to the L is equal to n over the GCD of n and L. So let's prove this fact. Now by proving that this set equality here, as we did also before, we will prove two inclusions. So for the first one, by writing our L as the GCD of n and L times k, where k is an integer, we can do that because, of course, the GCD, being a divisor of L, divides L, and so it can be written as itself times another integer to produce L, and so we can write L in this manner. Okay, so now having this, we will have that A to the L will be equal to A to the GCD of nL to the k. From this, it will follow that the cyclic subgroup generated by A to the L is a subset of the cyclic subgroup generated by the GCD by A to the power of the GCD of n and L. Well, why? Because A to the L and subsequently all of its powers can also be expressed as powers of the GCD of n to the L. So all the elements of this set here will also be elements of this set here. So this is for the first inclusion. So now for the inverse inclusion, we will use Bezout's identity. In particular, what Bezout's identity says is that there are integers x and y such that the GCD of n and L can be written as x times as a linear combination of n and L, so as x times n plus y times L. Okay, but now if we have an element, so if we have A to GCD of n and L, we can write it as A to the x times n plus y times L, which is the same as A to the x times n times A to the y times L. Okay, but we can rewrite the leftmost element as A to the n to the x, and then we're going to leave the rightmost element unchanged like this. But being the order of A equal to n, as we suppose here, we'll have that this equality will be true, and so this will just be the identity. The identity to the x will just be the identity, and this reduces to A to the y times L. Okay, but what do we have here? We have that we can write the A to the GCD of n and L as a power of A to the L, in particular as A to the L to the y. So all the powers of the GCD of A to the GCD of n and L will also be powers of A to the L. In other words, A to the GCD of n, the cyclic subgroup generated by A to the GCD of n and L is contained in the cyclic subgroup generated by A to the L. And so in other words, these two cyclic subgroups coincide because we have proven both the inclusions. So we have proven one of two facts about this theorem. For the second one, what we want to show is that the order of A to the L is equal to the n over the GCD of n and L. And well, how can we show this? Again, as before, we showed the reverse and the direct, say, inclusion, and here we will show with inequalities. So in particular, we see immediately that the order of A to the L is less than or equal to n over the GCD of n and L. Well, why? Because being the order of A to the L equal to the order of A to the GCD of n and L, what we have is that if we raise A to the GCD of n and L to the power of n over the GCD of n and L, we will get that this is just A to the n, which is the identity since the order of A is n. But because of this, this actually implies that the order of A to the GCD of n and L, that is the order of A to the L, is less than or equal to n over the GCD of n and L. Now, so we have proven one inequality direction. For the other one, on the other hand, let's suppose that maybe J is an integer less than n over the GCD of n and L, such that A to the GCD of n and L to the J is equal to the identity. So, okay, but if that was the case, notice that then J times the GCD of n and L would be strictly less than A over the GCD of n and L times the GCD of n and L, that is equal to n. So this will be strictly less than n. But by the definition of order, and of course we're supposing that this J is positive. So being this integer J positive and being it strictly less than n implies that there is actually no such integer J by the very definition of order of an element n. Why? Because the order of an element n is the least positive integer for which this equation is true. So for which A raised to that integer is the identity. And so we have concluded that the order of A to the GCD of n and L is greater than or equal to n over the GCD of n and L. So in other words, A to the GCD of n and L, which is equal to the order of A to the L, is equal to n over the GCD of n and L. And this concludes the proof. So now one might ask, how does this imply what we said earlier? And that is the fact about the generators of the addition groups modulo n, and in general generators for finite cyclic groups. And well, this is done by the several corollaries that this theorem has. So the first one, in a finite cyclic group, the order of an element divides the order of the group. This follows immediately from the previous fact that we've shown about the order of an element of a group. And for the second one, which is actually the corollary which will imply as a corollary of itself we could say the heuristical reasoning that we made before, it is the following. In particular, we will have that given an element A in a group G of order n, then we will have that the cyclic subgroup generated by A to the I will be equal to the cyclic subgroup generated by A to the J if and only if the GCDs of n and I and n and j are equal. And of course, this also holds for their orders. So also the order of a to the I is equal to the order of a to the j if and only if GCD of n and I is equal to the GCD of n and j. So for this, let's give a proof, which is pretty quick and short, but let's give it. So in order to prove it, we notice that a to the I by the previous fact is equal to the a cyclic subgroup generated by the GCD of n and I, and similarly the cyclic subgroup generated by a to the j is equal to the following. Okay, but now what we wanted to show here is that these two are equal if and only if these GCDs are equal. So saying that these two are equal is the same as saying that these two are equal. Okay, but now let's first prove the reverse implication. So let's suppose the GCD of n and I is equal to the GCD of n and j. Well, then trivially these two groups are equal because their exponents are equal, and so we have verified our statement. But for the forward direction, on the other hand, we have that supposing that these two groups are equal, then we have that their orders are equal, because trivially two groups that are equal have of course the same number of elements. But we have derived a formula for these two quantities in the last theorem, and it is equal to n over the GCD of n and I on the left hand side, and here it is n over the GCD of n and j. But dividing both sides by n and then flipping both sides yields GCD of n and I is equal to the GCD of n and j. This equation here, which actually concludes the proof, because we have obtained that these two things are equal if and only if these GCDs are equal. And so now we see immediately that as a immediate corollary of this, by just taking I to be 1, then we have that for an element of order n, so let A be an element of a group with order n, then we will have that the cyclic subgroup generated by A, which is a to the I where y is 1, is equal to the cyclic subgroup generated by an element a to the m, we can say. Then these two are equal if and only if the GCD of n and m is equal to 1, which is the GCD of 1 and n. And of course we also have that the orders are equal if and only if this is true. Okay, but now let's see how this implies the observation that we made earlier when we worked with addition groups modulo n. So let's see, we said that K generates Zn if and only if it is co-prime with respect to the modulo of the group. Okay, but we said here that we said here this condition about the equality of cyclic subgroups generated by elements of a group with the GCD. But now we see that an element k in Z to the n can be just written as k times 1. And, well, 1 spans Zn for all n. So translating that more general theorem in this setting here, it is equivalent to saying 1 times k, which is 1 to the k in multiplicative notation. So k times 1 is equal to 1, which is equal to Zn if and only if the GCD of n and k is equal to 1. And so with this we have actually found a condition for the generators of addition modulo n groups. And this is precisely what we wanted to do. So we have now obtained that these observations that we made before with these examples are actually true in general. And so we have obtained a theorem that claims this. So I think that now it is time to conclude this video because it's getting pretty long. But in the next video we will continue our discussion about cyclic groups. In particular, we will prove a pretty important theorem about cyclic groups that is known as the fundamental theorem of cyclic groups.